Okay, welcome everyone to this continuation of machine learning in mathematics. So how can you use machine learning to advance mathematics? And yeah, today I would like to tell you about part of the story which is already really successful. So there are plenty of quite exciting new research works in this direction, and I just focus on one as usual, because it's somehow easier to build everything around one example than just giving it's kind of easier to build something around one example, and I think this is a nice example. I'm not 100% convinced if it's the first example of its kind, probably not, but this is the paper I'm going to talk about, Construction in Combinatoric Neural Networks, which is a very nice paper by Adam Wagner from DeepMind, I guess. Yeah, and it's about this idea of anti-conjecture. So clearly the anti-conjecturing doesn't originate in the mentioned paper, but the example I'm going to give you originates in the mentioned paper. So what is anti-conjecturing? I'll tell you what anti-conjecturing is, don't worry. But also a disclaimer here, it's my word, I came up with it, so it's certainly not standard terminology. But I kind of like it, so I will stick with it. Yeah. So what can you do if you don't like it? Just click off this video. Very easy. So what is anti-conjecturing? Well, what is conjecturing? Conjecturing is really a key point of all of science and maybe of all of life. Maybe in more real world, conjecturing is called prediction. It's kind of the same. Conjecturing, prediction, it's kind of the same. Prediction maybe more in the sense of based on some evidence. Yeah, not a random prediction. You could also make a random conjecture, I guess, but it might be disproven very quickly. But yeah, conjecturing is kind of a key thing, whether you conjecture whatever the prediction of the stock market, or you make like a real conjecture, not a real conjecture, a mass conjecture. So the most famous mass conjecture, there should be a list, there should be a list of conjectures on Wikipedia, I guess. List of conjectures, of course there is, because everyone likes conjectures. And so the list of conjectures, and what is the most popular one? Let's just order it by citations. It's clearly the Riemann hypothesis. It's like clearly the Riemann hypothesis, yeah, no doubt. But I thought that was too difficult, so nobody understands what that is anyway. Even defining it is a bit tricky. I mean, there's some certain zeros of a certain crazy function that need to be somewhere. I'm pretty sure you're pretty fine with that, but if you just think about it, it's kind of already a conjecture that's difficult to state. So on my slide, I went with the second most cited conjecture, the Goldbach conjecture, which is like really simple to state. Every even number that is not 2, so 4, 6, 8, whatever, is the sum of 2 primes. Right? Easy to state conjecture, and extremely crucial in the history of mathematics, the Goldbach conjecture, the sum of 2 primes types conjecture, and it's based on a lot of evidence. So here, the number of ways to write something as a prime, you can see that this grows. So it's kind of very unlikely that the conjecture is actually wrong. So that's a good conjecture, right? You make a good conjecture based on a lot of evidence. Whether this is real world or not depends a bit on your flavor. But the key here is to say that again. I know I sound like a broken record, but usually just repetition is practice makes perfect, right? So repetition is not so bad. Conjecturing, essentially, if you've watched several other of my videos, essentially my point is math is all about good conjecturing, because a good conjecture should trigger research, should trigger discussions, should trigger people thinking about it, and that's really what research is all about, right? People just discussing and thinking about problems. So yeah, good conjectures are extremely important. Let's just stay in mathematics, because that's where I live. So conjectures in mathematics are just really, really important. So what is then the anti-conjecture? Is it something that is super unimportant? No, well, depends. But what I call an anti-conjecture is essentially disproving a conjecture, yeah? So anti-conjecture, disproving a conjecture. And an example, so I wasn't quite sure, in the history of mathematics, most conjectures so far turned out to be right, but it's probably going to change. So the way I cooked up, well, whatever my anti-conjecture would be is I just ask AI several of them, and they all gave me the same answer, the Euler sum of powers conjecture, which essentially just states that this is something that looks like Fermat's last theorem. Nothing difficult, looks like Fermat's last theorem, and then with computer help in the 1960s, they eventually found a reasonably large counterexample. So 144 to the fifth power is, I think, a quite large number. 145 to the fifth power. Yeah, let's call it a large number. And the whole point here is that this was true, or proven. Of course not proven. Evidence was collected for small values. Well, that's where the conjecture came from. And yeah, eventually it was wrong. So why is this an anti-conjecture? This is an anti-conjecture because it falls under the small number coincidence. Yeah. So small number coincidence means that if you check a million cases or whatever, and then you're happy and conjecture it, you might still have a small number of coincidences, and it actually is quite wrong. Yeah, and here you can observe that essentially you only needed to find those numbers, and then this, of course, just falls apart immediately as soon as you have those numbers. But finding those numbers is not trivial at all, because 144 is already to the fifth power is already quite a large number. Yeah. So anti-conjecturing is this idea of disproving a conjecture because the conjecture is falling into the trap of the small number coincidence. Yeah? You checked something a million times and it's still wrong. More in terms of life. This happens in life as well, by the way. Just replace a million by 5. You just check something 5 times and it's still wrong. And it just happens from time to time. And maybe, because it is a small number coincidence, you could try to train AI to find those large things. In this case, this was not AI. It just did a brute force search on all the possibilities. But for other conjectures, there might be just too many possibilities to do a brute force search. So you need a little bit of a smarter way of doing it. And let me now introduce you to a conjecture, and an anti-conjecture, and how it was disproven. Turns out that in graph theory, people in graph theory like conjectures. Other mathematicians, in my experience, are a little bit more careful when they talk about conjectures, which both of them has their advantages. Yeah? If you have too many, in graph theory, you have quite a few number of conjectures that are wrong, so they refute them all the time. Still, I would think that's actually good because the conjecture triggered research, but other people might disagree. A conjecture should be essentially fool's proof or whatever, but it doesn't really matter. In graph theory, you have a high number of conjectures, so no surprise here that the first thing you would try if you would try to run AI on an anti-conjecture is you would try something in graph theory. Not a big surprise here. Just a story from myself. I was once writing a paper and we had a big discussion with my co-authors whether we want to call something a conjecture or a question. I think we ended up calling it a question and not a conjecture. So there's something mathematicians somewhat don't like to write conjecture. The word conjecture. Anyway, because it might be wrong, right? Anyway, so here's a standard conjecture. So it's like in graph theory, you have plenty of conjectures of that form. Maybe not millions, a bit overshooting, but hundreds of conjectures of that form. So essentially, what you always do in graph theory, a graph is a matrix given by its adjacency matrix. So like in this example here, 1 is connected to 1, 2, and 5, and to 1 it's connected twice. So 2, 1, and so 1, 2, and 5. So this is how you get to the adjacency matrix. And as soon as you have a matrix, your head should just scream linear algebra, linear algebra, linear algebra. If your head doesn't do that, then it's probably not the right time to click off this video. So just kidding. You could still click off the video whenever. You could click it off whenever you want, by the way. Hopefully it was entertaining so far. So linear algebra means essentially you run linear algebra tricks now on graphs. Yeah. So like eigenvalues, eigenvectors, all that kind of jizz. Yeah. So eigenvectors of adjacency matrices are well studied. And there are like a zillion types of different formulas and whatever and type of conjectures. Something similar here, in particular for this example that I picked out. The distance matrix is essentially just a matrix of the distances. So if you have a graph, something like here's a vertex, one, here's a vertex, here's a vertex, and they are just connected like that. Very boring. You would get a 3 by 3 matrix. So 1 is distance 0 from itself, is distance 1 from 2, and it's distance 2 from 3. 2 is distance 0 from itself, 0 is also distance 0 from itself. It says a 1 here, 1 here, 1 here, and a 2 here, right? So the distance matrix. And you have a matrix, not quite the adjacency matrix, but something very related. What do you do if you have a matrix? You take its eigenvalues, the spectrum. This should be a lambda. And then there's another value, which I'm not going to explain, not so important. Another numerical value, a number that you associate to a graph. It's called the proximity. And then the conjecture says that certain eigenvalues, no, it's not readable anymore. How do we fix that? So certain eigenvalues, so this is the lambda, depending on the diameter of the graph, so the radius of the graph, are of a certain scale, right? They're not too small. This proximity, whatever it is we'll see it. I pull it up. But the proximity, whatever it is not too small compared to the eigenvalues. And that's kind of standard type of conjecture you will find in graph theory. Some eigenvalue type conjecture on graphs. Some mixing some numbers on graphs. And yeah, looks reasonable, and people have checked that. So here there's some evidence here. So D is 2/3 of the diameter, and this is actually true if I would let D to be a half of the diameter. Yeah? Then it would be true, and it's wrong if D is, so here it checks out, and if it is wrong if D would be the diameter itself, that is wrong. So somewhere in between there should be this breaking point, and yeah, people conjectured it to be around 2/3 times the diameter. Okay, fine. What is important here? Well, this is a conjecture interesting. The conjecture itself is okay. More the overall style of conjecture is what you would expect in graph theory, and the overall way to disprove it is just absolutely fantastic. And we are going to do this now. Again, this is based on this paper. Let's just open it because they essentially also define the proximity for us. It's a really nice paper. They have many more things going on. It's just one of the examples of this paper. I need to scroll down a little bit. So here's our conjecture about the proximity. So the proximity is like you take the vertex that is closest to everything, and that's essentially the proximity. And you just take the various distances. And here's our little conjecture. And the way to disprove it, it's kind of fun. It's kind of really beautiful. So you train a neural network using reinforcement learning. So you're giving it points. If it kind of finds small values, you give it more points. If it finds a graph where this guy is small, why small? Because you want it to be negative, right? So where this guy is small, you give it some reward and then rerun it again. And eventually it will find a picture like this, which is like really nice because, this is not, it says it explicitly, the proximity is small, 0.4, but not quite a counterexample, but you're still very happy because you can essentially look at the evolution of what the neural network gave you, and it crystallizes out that you essentially want something that is like on the line, and then there is this one vertex which is very close to everything, and a little bouquet around. Okay, so that's something you can try, and then you do by hand, can do a larger number here, whatever n equals 50 or something, number of vertices. Try the same, and you realize, this gets even smaller, and it gets even smaller, right? So the computer gives you kind of a good potential anti-conjecture, but not so a potential counterexample, but not a counterexample itself, just a pattern that you should expect. And that's the whole point, because neural networks can recognize patterns. And then you can go by hand and essentially find a very large, so here are the 190 leaves of this type, a very large type of graph on 203 vertices, where then actually it turns around and gets negative. Yeah? So that's what they did in this paper. So they trained a neural network via reinforcement learning that gave us almost counterexamples, where our value that we want to see negative, we essentially minimize that value, and you somehow give points, I say it again, if the neural network is doing well in this in this fashion, and it will learn and learn and learn and learn at the point, and eventually you see a type of pattern emerging. So the paper has kind of another problem, which is not quite, it's not the same, but somehow the idea is the same. You run a neural network, you train it, and then eventually, after training, a pattern will emerge, right? And yeah, from there on, you can essentially just generalize the pattern and prove things by hand. Okay, say it again. Use the neural network to get an idea how a counterexample could look like, and then you go and prove or try to find one by hand because there's a small number of coincidences, and eventually things actually tip over. It's kind of a very nice idea and like very applicable in general. So here's another one of those from a different paper. Essentially, you want to minimize a certain value in the number of vertices, n is the number of vertices. You already know that it's bounded by some abstract reasons. So this guy here is roughly the 0.35. So here's the lower bound, here's the upper bound, and then people did by hand, trying to minimize it, and eventually the neural network approach where you play the reinforcement game will do better. So here on 200 vertices, you are closer to the minimal bound here. No? So that's the whole point of this anti-conjecturing, trying to not really finding a counterexample, but finding a blueprint for the counterexample. And that's actually a really cool idea and works pretty well. Anyway, I hope you enjoyed this video, and I also hope to see you next time.